As I mentioned before, the goal of synthesis is to build complex molecules from simpler and cheaper ones. Or sometimes we will convert the specific functional groups to another ones. In order to begin practicing synthesis problems, it's really important to know all the individual reactions that we covered so far in this course. So we learned about substitution, elimination, and addition reactions in alkenes and alkynes, and we are going to use our knowledge to solve the synthesis problems. So you are going to see different types of synthesis problems in this course. The first type that I already talked about in the previous videos about is the sequential synthesis problem. And as I mentioned before, to answer such questions, you need to look at the product and the starting material for each step, identify their differences, and think about the reagents that can accomplish the specific transformation for you. Now let's look at the first example here. So as I mentioned, we need to compare the starting material and the product for each step. So in this step, I have alkyl halide, which is converted to an alkene. So that reminds me of elimination reaction. So elimination reaction happened here. Now, when we are talking about or thinking about elimination, we need to think about beta proton abstraction, formation of double bond, and loss of leaving group. So I first need to find my beta protons. And I have two types of beta protons in this structure. Now, if this beta proton was abstracted, I should make a double bond here with the loss of leaving group, which forms the more substituted alkene, which is a Zaitsev product. However, that beta proton was abstracted to form a double bond here between these two carbons, and the leaving group left the molecule to form the Hofmann product. So the product that I have is a Hofmann product. Now, if you remember, in order to form the Hofmann product, we need to use bulky base, such as tertiary butoxide. Now, if you look at the next step, so I have an alkene, which is converted to the alcohol. So basically, I have added OH and hydrogen across the double bond. So the hydrogen is not drawn, but I know it's there. Now, addition of OH and hydrogen across the double bond can remind me of hydration or hydroboration oxidation of alkene. Now, if you look at the product, OH was added to the less substituted carbon, which is anti-Markovnikov addition of OH and hydrogen across the double bond. And if you remember, the reagent that can accomplish this for me is BH3 THF in the first step and hydrogen peroxide, sodium hydroxide in the next step. So it is hydroboration oxidation of the alkene. Now let's look at the second example. So again, let's compare the starting material and the product. So again, I have alkyl halide, which is converted to the alkene. So I need to think about elimination again. So this is elimination process. And when I am thinking about elimination, I should draw the beta protons. So the beta protons, I have one here, and there is one here which is drawn. Now the double bond is formed between these two carbons instead of this carbon. So this double bond here forms the more substituted alkene, which is the Zaitsev product. So the product that I have here is Zaitsev product, and I know that small bases such as sodium ethoxide or sodium methoxide can accomplish this transformation. Now in the second step, so I have an alkene which is converted to the diol. So I added two OH groups across the double bond in the seen fashion. So I have cis diol here. So we have addition of two OH groups across the double bond. Okay, it's a seen fashion process. Now if you remember, we had two sets of reagents that can accomplish this transformation. One of them was use of osmium tetroxide and the other one was use of potassium permanganate. So you can write either of them. So I will write osmium tetroxide, catalytic amount, and use of NMO. So we can complete this transformation using these reagents. Now let's look at another type of synthesis questions that you may see. So in these types, not only you need to find the appropriate reagents to complete each transformation, but also you need to find the structure of missing molecule in the middle. So basically this molecule will act as a substrate in the second step of this synthesis and as a product in the first step. Now to answer these type of questions, the very first step is to find this missing structure. And in order to do that, I suggest you to start with final product and think backward rather than starting from the first starting material and thinking forward. So how are we going to do that? Let's look at the first example. So by looking at the final product, I can see a transdiol. So I have a transdiol here. And according to my knowledge, I know that I can make a transdiol out of an alkene. So in this box, I need an alkene. So basically, we added two OH groups across this carbon-carbon bond in anti-fashion. So if I put a double bond between these two carbons, I can have my desired alkene as a starting material. So this is going to be the missing structure in the middle. Now, in order to convert this alkene to the transdiol, I know we have a reagent, so we can use proxy acids such as MCPBA in the first step, and in the second step, we can use some sort of acid, so I write H3O plus, to accomplish this transformation. Now let's look at the first step and find the appropriate reagent. So since the missing structure is found, we just need to compare the starting material and the product and think what's happening and what type of reagents can help me to accomplish this transformation. So here in the starting material, I have an alcohol, and in the product, I have an alkene. So basically what happened, this OH group has left the molecule. And we know that OH is not a good leaving group, so basically what we did, we convert OH to the good leaving group first. And since I made an alkene, elimination reaction must happen. Now I know we had two ways to convert the OH. to the good living group, I'm going to use toctyl chloride and pyridine to convert OH to the tocylate molecule. And then I need to get rid of this beta proton, form a double bond, and then living group leaves the molecule. So I can use some sort of base, strong base, such as sodium methoxide. Now let's look at the second example. So the final product in the second example is an alkene. So we formed an alkene here. And therefore we need to think about the process which we call elimination. So the product for elimination is an alkene. Now in order to find the appropriate structure here, we know that a double bond is formed between these two carbons. Therefore one of these carbons should act as an alpha carbon and carry a good living group on it, and the other one should act as a beta carbon that has beta proton attached to it. So I would take this one as alpha and this one as beta. As I mentioned, in the alpha carbon we should have a good living group such as bromine attached, and in the beta carbon we have beta proton. So the starting material for this transformation can be an alkyl halide. Now, what type of reagents can we use to complete this transformation? So looking at this alkyl halide have two types of beta protons. One is here, which form this product for us, and the other one can be here. Abstraction of this beta proton would form basically the more substituted alkene, which can be a Zaitsev product for us. However, this beta proton was abstracted to form our desired product, which is the less substituted alkene. So this alkene is a Hoffman product. Therefore, we need a bulky base such as tertiary butoxide to complete this transformation. Now, if you look at this starting material and the product for that, so we have an alkene that is converted to alkyl halide. So basically that double bond is gone, and instead we have bromine and hydrogen attached across the double bond. So we have hydrogen here, and again if you compare these, hydrogen is added to the less substituted carbon and bromine is added to the more substituted carbon. So this is a Markov-Nikov addition of hydrogen and bromine across the double bond. And in order to complete this process, we need a reagent such as HBr. So this is hydrohalogenation process. Now a question that can be asked here is, why did I take this carbon as alpha and this one as beta but not in reverse order? So if I do that, meaning that I take this one as alpha and this one as beta, I would get this alkyl halide, which is a primary alkyl halide, and I know the process here is elimination process. And according to our knowledge, we know that elimination always prefers tertiary substrate and sometimes secondary substrate, but it is not happening with primary substrate. So this transformation cannot be accomplished. Now let's look at another type of synthesis question. So we have the starting material and the final product, and we have a few sets of reagents as options, so we need to decide which option can take us from this starting material to the product. In order to answer these type of questions, you need to examine each option and decide whether the sequential reagents that are listed there can take you to the final product or not. So in the first option, the first reagent that were used was sodium methoxide. So sodium methoxide can react with this substrate. So since it is secondary, elimination with sodium methoxide can gives us the major product. So for each step you need to consider the formation of major product, and we are going to form the Zaitsev product because sodium methoxide is a small base, so it can give us the Zaitsev product. Now in the second step, we are using BH3THF and hydrogen peroxide, sodium hydroxide. So this reagent can add hydrogen and OH in anti-Markovnikov fashion across the double bond. So therefore, meaning that in anti-Markovnikov fashion, so OH should add it to the less substituted carbon and hydrogen to the more substituted one. So we are going to form this product. Now this product does not match our desired product, so this option is out. Now let's look at option B. So we have tertiary butoxide. We know tertiary butoxide is a bulky base, so we are going to form the Hoffman product with that. So again, elimination happened. But this is bulky, so we are going to form Hoffman product, which would be this structure. Now in the next step, we are going to use H3O plus. So we are going to add hydrogen and OH through Markovnikov addition. So meaning that OH will be added to the more substituted carbon and hydrogen to the less substituted one. So we are going to form again this product, which does not match our desired product. Now in the next option, option C, so this one is also out. So again, we are going to use sodium methoxide, similar to the first step. We are going to form Zaitsev product. Then we are going to use H3O plus. So again, we are adding hydrogen and OH across the double bond in basically Markovnikov fashion. So OH will be added to the more substituted and hydrogen to the less substituted carbon. So we are going to form this product. Again, this does not match the final product. Now option D. So we are using triethylamine. If you remember, this is the abbreviation for triethylamine, and triethylamine was also a bulky base. So we are going to form the Hofmann product again. And then we are going to use reagents for hydroboration oxidation. So BH3THF, hydrogen peroxide, and sodium hydroxide. And again, we have anti-Markovnikov addition. So OH will be added to the less substituted and hydrogen to the more substituted carbon. So the final product would be this molecule, which matches the final desired structure. So the answer for this question would be option D. Now let's look at another type of synthesis problems. So we have the starting material and sets of reagents. So we need to decide what the product look like after treating the substrate with these reagents. So in order to answer this question, we need to draw the product after treating the substrate with each reagent. So the first reagent is tertiary butoxide. I know tertiary butoxide is a bulky base. And the process that should happen here is elimination. And with bulky base, I will get the Hofmann product. So let's find the beta protons first. I have one type of beta proton here, one type here, and another one here. But since the alkyl halide is symmetrical, these two are identical. Now, in order to form the Hofmann product, the base, the bulky base, will attack the alkyl halide from the less crowded side, which is this beta proton. So I'm going to form a double bond between this carbon and this carbon. So the base will take the proton, forms a double bond, and basically kicks off the leaving group. So we are going to form this product. Now in the next step, we are going to treat this alkene with potassium permanganate, sodium hydroxide in cold temperature. And I know this reagent, so I'm going to add 2 OH groups across the double bond in anti-fashion. So this is anti-dihydroxylation process. So I'm going to form this product. So 2 OH will be added across the bond in the anti-fashion. Now, do I need to show the stereochemistry on this carbon and this carbon? No, because this is not a chiral carbon. These two sides are exact the same, and we have 2 hydrogens here. So we are going to form only one product. So this is our final product. If this carbon or this carbon was a chiral carbons, we need to show the stereochemistry, and we know the stereochemistry must be opposite because we are adding 2 OH groups across this double bond in anti-fashion from the opposite sides.